Hello, you're welcome to lecture 3 on the series of operating system concepts. Now, the question rises on why do tech students or computer engineering or computer science students need to study operating system? It's very important because they need to understand the way the computer system operates, and in such a way, it makes it possible for them to write their programs as developers. So, these are the reasons why operating system concepts are being discussed in most computer engineering programs. All right. We are going to get into another series, and this series is on threads. And this topic currently is going to be on threads and processes on threads. All right. Question now arises: why do I need threads? What are threads doing in operating systems? But every program needs to be executed, and being things that needs to be executed, it is while it is being executed, is turned into a process, and this process definitely creates threads because they are going to be working concurrently. Different processes are running concurrently and creating child processes and all that. So this is why this lecture is important. You're going to understand concept behind that whole how processes work. All right, is a breakdown. My name is Dr. Emmanuel Udoiwood. Please, if you have not yet subscribed to the channel, I beg you to subscribe to it, like it, and share it with your colleagues or any other person that you know could be very relevant for them, especially university students or tertiary institution students who are who should take exams. All right, they will take exams related to operating systems, people who are going for remote jobs, interviews, and those who are doing things that are related to IT certifications. They need to have an idea of how operating systems work. So please share, subscribe, and like. All right. Then if you have any question, I would like you to just drop your question in the comment section and I'll answer it for you. All right, let's dive into the lecture proper. Now, we look at principles of operating systems. Lecture 3, processes and threads. The outline will be process concept. We'll look at process scheduling, operations on the processes, cooperating processes, threads, and interprocess communication. Basically, the operating system is a variety of programs. And there are several programs that the operating system executes. So an operating system executes a variety of programs. One of them is batch jobs. Now, batch jobs are jobs which are being executed as they come. So, as a in batch systems, we call the processes jobs. We call each process or a job. Then each job arrives and is being dealt with before the next job is picked up and is being dealt with. That's how the system works it, and it gives output as it finishes its jobs. Then in time shared systems, we call the user programs, or they are being called tasks. That was this, right? Another term that was being used during the during time shared systems. Now remember, time shared systems means that you have one microprocessor, several tasks are available for it to do, and it works on them. And when it finishes one, once the time is up, it removes it and then picks another task. Just like you are working maybe on your project and you have given yourself a timer and you said after 1 hour, I'm going to pause reading and then start solving problems. Now, these are ways you are working, trying to make sure that your time works. It could be I'm sharing time for operating system. Then after operating system, I'm going to read database, and after database, I'm going to read something that has to do with the data structures and all that. So that's it. So job, task, and program are used interchangeably when we're talking about operating system process concepts. All right. Now, a process is a program in execution. Process execution proceeds in a sequential fashion. All right. It means that the process is executing. Once you start executing a program, we call it a process, and we have to finish one before we pick the next one. You can't have several processes being executed by the CPU at the same time. So one process has to be finished before the CPU picks the next process. Then we have the process contains what we call a program counter, start and data. Now, these are information. Program counter helps you to keep information about how many times it has worked on the system, where it's going to be stored in the system and all that. Then the stack tells it issues like memory location. Remember, we have different types of data types. Stack is a kind of data type also, where it works with last in, first out. So the last data that was pushed into a maybe a system. For example, you have this is a queue, and then on a stack you have different stuff, different processes are here, and then once the first one enters here, then before you can pull out something, you have to also pull out from this very stuff. So the last that was pushed in is the first that we pushed out. So we have what we call LIFO, LIFO mechanism. Then the data section contains all the data pertaining to that program. Now, the next question is: the process equal to a program? The process and program, are they the same thing? Well, they're very similar, like we have said before. Now, program could be written by you. You write your entire program and you finish, and then you define your some data, how your program is going to run. Now, usually, in your static, we are using a static memory. We use a stack, right? Where first in, like I said before, last in is the first out. So here, when in memory, like RAM, the main memory, which we already know is fixed size. For example, your RAM could be 4 gig, your RAM could be 8 gig, 40 gig. There's a fixed size. So your program knows that I have this fixed size, I can't work with more than this. So the process is stored in this kind of environment as a stack, and then picks out from there. But when we talk of a heap means that it does not really know the size. It could be an unlimited size. Usually your heap is tied to virtual memory, which could be in your main hard drive, okay? So while that is stored there, it means as you need each information, it pulls it out. Dynamic data is being kept on being heaped here, can be moved. Once you start executing on runtime, it moves from the heap, then stack, then keep on processing. So let's look at some concepts. Let's look at concept more to a process than just a program. All right, more to a process than just a program. A program is just part of the process state. All right, program is just part of the process state. If I open a text document on WordPad and you open it in Microsoft Word, you have the same program, which is the same text document, but on different processes. All right, so WordPad gives you a different process. I open it on Microsoft Word, or you open it on Microsoft Word, it comes a different process. We have another issue that a program can invoke more than one process. For example, a web browser launches multiple processes, and each one is a different tab. So you have that program, which is your browser, and is invoking different programs. All right. Now, a process has different states, diverse states. The process changes states as it executes. The initial stage is when it's created, and that is what we call the new state. All right. So we look at this. The new state is when it is being created. It has a running state. It has a ready state. The ready state is when it has entered into a queue and it is ready to be executed by a CPU. So it's admitted into the queue, ready queue. And once it is admitted into the ready queue, it's moved into the running state when it starts being executed by a CPU. Now, in case there's an interrupt, you can return it back to the ready queue, right? An interrupt could occur because maybe the time is up for it to execute. If the time shared system, we said time's up, you have only 3 nanoseconds to work, microseconds to work. After 3 microseconds, interrupt kicks in and it's returned back, and then another program picked up. Another state is the waiting state. In case maybe while it is running, it needs to do IO work or an event occurred. It needs to perform an event. For example, either it needs to fetch data from somewhere else or it needs to get data from the keyboard, then automatically it gets into a waiting state, and when it has finished the IO or event completion, it puts back into the ready queue. So the process can be in either the new, the ready, the running, the waiting state at any time while it is executes. Then once it's through, it now exits the system, and we call it that as terminated state. It has left the system. Now, so those are the different states: new, running, waiting, ready, and terminated state. Let's look at the process control block. The process control block contains information such as the process state. Remember, I just explained the process state. It contains information about the process number, the program counter, CPU registers. CPU registers is where it is being stored. Remember, it's memory. Scheduling information. It talks about, is it a process priority? It talks about how important the process is. Then you talked about memory management. It stores information about the memory management, where the memory, where this process is being stored, its base, its limit information, counting information, the input-output status information, the list of I/O devices that are located to this process. These are all part of the process control block. Representation of the process scheduling. When is, well, we're going to look at when does a process move, where it moves to, and then why it takes that decision move. All right. So here we are looking at the process as a process moves from queue to queue. There are different queues here. If you look in here, you see we have a ready queue and we have the IO queue. Ready queue is for processes who are going to the CPU, while IO queue are processes who need access to input-output devices. These are the two different areas you need to understand. Now, when a process is first created, and then from new it moves into ready queue where it needs to go to the CPU. When the CPU is free, it now moves from the CPU from the ready queue to the CPU. While it's working on the CPU, there could be an interrupt, all right? Or it could require some other information. So you will now ask for an IO request. The process will need an IO request, make an IO request. And once it makes an IO request, it is now moved to the IO queue. And then it stays in the IO queue until when the IO is available for him to use. Once it's completed, he's now returned back to ready queue for him to continue his work. Also, if while the process was being executed, then its time was up, it now enters into its time slice that expired. It's now returned back to the back of the ready queue for it to be stored until it's being executed again. But if its time slice was not up while it was executing and it completely finished, it leaves the system completely. So it leaves the system completely. Then the process while it was executing suddenly requires to create a child process, because that's where the instruction or the code says. Now, there is information, there is what we call fork a child, which means you're going to create some other, for example, you have one process from up here coming and creating 3 different processes. So these are its child process 2, and child process 3 is the parent process. So if it creates it, then the child needs to execute. And then all the child processes may need to execute and terminate before the process can complete. Or as it finishes each section, it goes back to the wait queue for more processes that are going to be executed. Another way that a process makes a decision is maybe while it was running, suddenly there was an interrupt, which means a process maybe with higher priority is available. So it has to wait for an interrupt. And once that interrupt is treated, it can now go back and line up for it to be executed again. All right? So these are some of the reasons why processes move from one. They move from, this is in running state, they move to waiting state, and then move to waiting state, before now moving back to ready state. These are the different states that it can move. Right, so we have here a device queue, as I said before, and these are the different processes in the device queue. They are all waiting for a device. Then in ready queue, they are all waiting for the CPU. So this is the ready queue where all the different processes are being stored. Now, this is a diagram where we have the ready queue and various I/O device queues. For example, you have the ready queue for our waiting to go to the CPU. Then you have the magnetic tape queue. All right. You have magnetic tape 0, 1. Then we could have the disk queue. And we also have the terminal unit queue. All right. These are the different queues that are possible. The ready queue and the different device and I/O queues that are available. Let's look at another topic, process scheduling queues. Process scheduling queues. A job queue is a set of all processes in the system. All processes within the system are within the job queue. Now, all the processes within the system can be stored in the hard disk because they are much, and then moved gradually to main memory. We have the ready queue. These are a set of processes residing in main memory, ready and waiting to execute. Usually your main memory is made up of your RAM, your cache, and some other registers, all right? We made the different levels as we move, as we proceed. You have device queues are a set of processes waiting for an I/O device. Process migration between the various queues is possible, as I have shown you earlier, because they are moving from one state to another. Then there are different, these are the queue structures, is made up of data type, usually linked lists. For example, if you see here, we have a linked list that controls each of these registers. All right, they are all linked to each other here. We also use the circular lists and other lists, and those are some of the list structures that are being used there. Now let's look at enabling concurrency and protection, the multiplex processes. Now, concurrency process means that multiple processes can happen together or rather in parallel. The question now comes in, how do you make sure that there is no problem between one and the next? So we are looking at concurrency and protection here. One and only one process is active at a time. Only one process is active at a time. So we have the current state of a process is held in process control block. The moment we pick that process, the current state of that process is being held is being written in the process control block. For example, it could be red is running. And once it starts running, no other process should run. So that's one process being active. Once one process has entered running state, no other process will enter running state. Especially when we're talking of a single CPU system. So the snapshot of the execution and protection environment, that's just how it happens. The process needs CPU resources. So that process that needs CPU, once you get the CPU and its resources, no other process gets those things. So allow that process to run. Another way of handling that and protecting from each other is what we call scheduling. You give out the CPU time to different processes. You give out CPU time to different processes. So a process knows that only one process is running at a time. Give more time to important processes. So important processes will have more time or higher priority, as we said it earlier. Then another way is protection. To protect, to make sure that we give piece of resources to different processes. So if a process wants to execute, you give it its memory that it needs to work with. All right. If it needs I/O devices, you give it its I/O devices. The operating system gives it controlled access to non-CPU resources. You don't allow two processes to have the same memory address at the same time. Nope. One process works only within its own memory. So if it's working in register location A, no other process stays in register location A, just that process. That's how it protects it, so that one process does not clash with the next process. That's system planning and scheduling. Now let's look at the term context switching. Remember that we have multiple processes working with only a single CPU. Even if it's multiple CPU, the processes are always much more than the CPU. So there needs to be a way to switch one process and load up another process. Now, context switch, task that switches CPU from one process to another process. That means the CPU has to be given different tasks. For example, if CPU is working on process A, after a while it has to switch to process B. So the CPU must save the process control block of the old process and load the saved process control state of the new process. Remember that. So if this is process A, it has to be saved and process B loaded into the system. Right? The system must do that all the time. It must save the PCB state of the old process and load the PCB state of the new process. Remember that keep saving each of them at all the time before you load the new one. Now, context switch time is overhead. It's also a burden on us. It's not a burden on the operating system because it takes time to do that. And it's a time that during that period of context switching, the CPU actually does nothing during that switch. So we call it, it's seen as an overhead. It's a little inefficiency. The system does no useful work while switching. That's what happens. The overhead sets minimum practical switching time and can become a bottleneck. So there needs to be a practicable, very short context switch time so that it does not delay processes from happening, all right? Time for context switch is dependent on the hardware support. So we have between 1 and 1000 microseconds can exist. So if you have a faster system with hardware that handle things like context switching, it's much faster and better than a system that everything is just being done with a smaller RAM. So with a 40 gig RAM, 50 gig RAM system, it will be much more smoother compared to a 4 gig RAM. That's why, issues of memory and issues of CPU speed are very important. We also have the concept of different core of operating systems. So while one is doing context switching, you could pick another process that is very short, run it while the switch is going on. All right, so now CPU switch from process to process, as I explained earlier. And here we have process P0, and we have two processes, P0 and we have P1, P0 and P1. And then this is how the operating system works. While it's executing P0, it sees that there's an interrupt or a call for it to pick process P1. So it first of all has to save the state into move PCB, save state into process for PCB 0. All right, it needs to save it. And within this period, the CPU becomes idle. It doesn't do anything at all within this period. So it loads the state from process 1. So it loads the process control block of process 1 into the system. And once it does that, it now starts executing again. So this is when the CPU becomes busy again. Then once it's through, there's another system called, it should load process 0 again. So when that system call comes up, or that interrupt comes up, it saves the state of the process control block of process 1. And within that period, it's saving, nothing happens. So the CPU does not do anything. It just, that's why we call it overhead. And then after that, it now loads the process control block of P0 into the system again and starts executing. So the period from when it picks A and loads, saves process 0 and loads process 1 is called context switching, right? Now the code executed in the kernel above is overhead, as I said before. Overhead sets a minimum practical switching time. So the try is the hardware that helps. The faster your hardware, the shorter the context switch time. Schedulers. What are schedulers? Right? Schedulers help to plan how jobs move from one place to another. So there are different types of schedulers here. We have the long-term scheduler, the short-term scheduler, and we also have the medium-term scheduler. Now, the long-term scheduler sometimes is also called the job scheduler. The long-term scheduler selects which process must be brought into the ready queue from the job queue. Remember I said that all jobs are in the job queue, and your job queue could be created within your hard drive. Now, the long-term scheduler picks it from the pool of the job queue, picks it from the pool, and then sends that job into the ready queue. And your ready queue is usually in your working memory, your main memory. Now, it is invoked very infrequently, that is in seconds or in minutes, and it may be slow because it packs so many jobs at a time. It doesn't need to pick one job. It can pick groups of jobs, could pick 10 jobs at a time and all that and load them. As long as there's space in the ready queue, it loads them there. It controls the degree of multi-programming. It controls the degree of multi-programming because of the way it mixes the way the programs come in. For example, you could have I/O jobs that will be doing more of input-output tasks. It controls those that will be also, then they also have tasks that will be doing more of execution. Remember, we call some I/O bound jobs, but we all call some CPU bound jobs. So it must control the degree of how that multi-programming works so that we don't have too many jobs that will be bombarding the CPU, and we don't have too many jobs that will just be doing I/O work and leaving the CPU starved, right? So these are some of the, that's what the long-term scheduler does. Then we also have the short-term scheduler or CPU scheduler. The CPU scheduler selects which process should execute next and allocates CPU to it, all right? It is invoked very infrequently in milliseconds and must be very fast. Sometimes it is the only scheduler in the system. So the CPU scheduler or short-term scheduler just picks the job from the ready queue and allocates it to the CPU. It picks it and allocates to the CPU. It keeps on doing that. So it picks so many jobs. The CPU, remember, just processes jobs in milliseconds. So it picks it and dumps it. The CPU runs it and then releases it and gives it, picks another job. Then we have the medium-term scheduler. The medium-term scheduler is not very common in many operating systems, especially personal operating systems. So what it does is that it swaps out process temporarily. It swaps out processes temporarily and balances the load for better throughput. Now, the way why it needs to swap out is that sometimes you could have it has seen that there is so much CPU bound processes. And if there's so much, then the medium term kicks in, pulls out jobs that are some of the CPU jobs and pushes in some of the jobs that are IO bound. So you could have jobs that are working towards IO and jobs that are moving towards the CPU. So that the CPU is not overloaded while the IO does nothing. Just helps you to do that better mix. So it swaps out processes. So let's look at the medium term scheduler or on a time sharing system. Now, this is our ready queue, and then it pulls out the ready queue. Let's say short-term scheduler, CPU scheduler picks a job and drops it on CPU. And once the process is running, maybe this time medium-term scheduler swaps out the job. So the job is swapped out. A partially executed swapped out process is swapped out and into the ready queue. Maybe it could be that your time is up. And once the time is up, it pulls it out and puts it at the back of ready queue. Then maybe it finds out that there is an IO waiting to be executed. So it swaps that process out and picks it and puts in the IO waiting queue for it to find IO and then puts it back into ready queue once that is done. So it now eliminates the short-term scheduler from doing this task. Its job is to pick jobs that need to go into waiting queue or need to have timed out and put them back into ready queue. So that's just kind of what it does. It handles these processes. Now, this is an example of a tree of processes in Linux. So in Linux, we have this is usually the first process, the init process. That's usually the parent process. And this parent process can create multiple child processes. For example, here we have login, kthread, and SSH. We have different types of processes that are being created as a process is going on. Now that's what we call the parent process here, and here we have the child process here. All right? I explained earlier, mentioned items such as I/O bound processes, CPU bound processes, and all that. So let's look at process profiles. I/O bound process spends more time in I/O. It spends more time doing input output, like it needs something from the keyboard, it needs to be shown in the monitor, it needs a printer. Those are all I/Os. Usually has short burst CPU burst, short CPU burst. It doesn't spend time doing CPU work. It spends more time doing CPU job. Here the CPU is usually underutilized. Then we have the CPU bound process. The CPU bound process spends more time doing computations, very long CPU burst. That's what it usually has, and uses a very low I/O. So the I/O becomes underutilized for a CPU bound process. So usually the long-term scheduler has to do a right job mix. So a long-term scheduler admits jobs to keep load balance between I/O and CPU bound processes, as I explained earlier. Then the medium-term scheduler ensures the right mix by sometimes swapping out jobs and resuming them later. So if you have, while it sees a job, just like I had said earlier, and a job is running on the CPU that we had here, this job was running on the CPU, and while it was executing on the CPU, it needed I/O job. Now needed I/O, to communicate with the input output device. Then the medium term scheduler automatically pulls it out and puts it in the I/O queue. All right. So that is a way of making sure that you don't waste time and delay while you are looking for CPU, or then you hold on other processes. Now, let's look at the process scheduling. Process scheduling. Now, process creation. Processes are created dynamically. Processes are created as process is being executed usually. So a parent process may want to create child processes while executing. So that means dynamically as it goes on, it's being created. So usually you could have, for example, you could have a situation where somebody, and writing within your program, you have situations and say, if this condition, then do this. Now that automatically creates a child condition to check for conditional statements. Or it could check for, it could be a loop somewhere that has to be done within the conditional statement. Now those automatically create child processes. So those child processes are things that needs to be handled. So a process which creates another process is called a parent process. And the created process is called a child process. Right? So usually the result is a tree of processes. For example, in Unix, we have processes that have dependencies and form a hierarchy. I had shown you an example earlier. And each of these processes requires resources when they are being created. So resources required when creating processes. The resources are CPU time, files, memory, I/O devices, and more. So these are, we'll talk about process creation. So this is an example of the Unix process hierarchy. In the Unix process hierarchy, you have the core user. It could be the root. The root is usually the primary user, the core user. Let me say user, you have the page daemon, you have the swapper, you have the init. Now, the page daemon deals with pages, okay? It manages the different pages that are involved in every process. Every process is a page, right? Is a page which has been created, and that page will be moved into main memory. Then you have the swapper that moves one page from one environment to the other. You could move it from the main memory to the cache or to the registers. Then init is our parent process that creates other sub-processes. These are child processes that are going on here. All right. So just like we said, the root is the user account. The super user creates files, deletes, installs programs. And we have this page daemon that moves memory pages. We have the swapper which picks processes and runs. Then we have the first process created, the parent process, and we have the child process. What does it take to create a process? You must construct a new process control block. That is inexpensive. Then, secondly, the operating system must set up a new page table for address space. There must be a new page table for address space. A page table is similar to an Excel sheet that keeps tab of the information of where each process page is, where each process page is located. So this is more expensive because we are now using a resource. To create a process, a new process is not really hard. Doesn't need much resource, but now when you start talking about page table, we are now talking about allocating spaces. Start using resource. Then you copy data from the parent process. All right? Copy data from parent process. In Unix, when you use the term fork, it creates a process and copies, data from the parent process. Now, there's something we call the semantics of Unix are that the child process gets a complete copy of the parent memory and the I/O state. It's originally very expensive, but it's much less expensive with a copy on write. All right, so it is when it is being created that the parent does this copying, right? So, but there are other operating systems that do not really need to copy everything from the parent. Okay, there's a parent is kept in the resources that are needed are being kept somewhere, and the child will also access that information. It doesn't really need to copy it into its own PCB and all that. Now, the copy the I/O state like file handlers, and this also causes a little bit of takes up some spaces because some I/O devices have to be set aside for it to use. So when we talk of the cost, we are talking of the cost to the resources which are going to be utilized when you create each process. In terms of, we're still on process creation, we look at resource sharing. Parent and children share all resources. Children share subset of parents' resources, and this prevents many processes from overloading the system. Right? These are the different ways in which process scheduling are being handled. First one is that the parent and children share all the resources. All right? Parent and children share all the resources. Children share some of the resources of the parents. So this prevents many persons. The parent and children share no resource. That's another type of resource sharing. It's possible the child does not need to share any resource with the child. Right? Now, during execution, the parent and child execute concurrently. Right? Sometimes the parent and child needs to be executed while the parent is executing, the child is executing and giving solutions to the parent to keep on. So then also there are other ones that the parent waits until the child has terminated before it continues his own execution. So it waits until that. Then there are also situations where if a parent terminates before the child and becomes orphaned, it gets inherited by the grandparent. All right. So if you have a process that has different layers, and then the let's say you have the first, the parent, the second layer, okay, let's say the first child and then the second child. So by the time there's a second set of children, automatically that has entered a situation where you have the grandparent. So let's say we have a situation here where you have the parent, having child. Let's do it here. The parent having the child processes, and the child processes now having more child processes. So in case this parent terminates, this child automatically be inherited by this grandparent. So this grandparent now starts dealing. So it's now under this grandparent. In terms of the address space, the child process is duplicated. It's a duplicate of parent process. The child process is a duplicate of the parent process. The child process has a program loaded into it, right? So the child process must also be given its own address space to work, even though it's a duplicate of the parent process, but it's given its own address space to work. In Unix process, there are two keywords. We have the fork system call, and we have the exec CVE system call. All right. Just do it by giving some examples. All right. For example, we have here fork system call creates a new process, creates new processes. Imagine your program is a photocopier. When it calls fork, it makes an exact copy of itself, like a clone. Both the original, which is the parent, and the copy, which is the child, start running the same code, but now as two separate processes. All right? Just duplicate itself and keeps working. Then exec system is used after a fork to replace the process's memory space with a new program. Right? So imagine you are watching a YouTube video, which is a process, and suddenly you click a link that opens a completely different video, but in the same tab, in the same browser tab. That's what exec CVE does. It replaces the current program in the process with a new one. No new tab, no new process, just full switch. Those are different process creation. The other one terminates what was going on and replaces with a new process completely. With a new task completely. Just does, you move to a different tab, the same tab, but it moves to a different website. While fork just keeps on creating a duplicate of itself and runs. Right? Let's look at process termination state. Process executes last statement and asks the operating system to delete it. Then it now exits the process. The output data from a child to parent can be a child that wants to end his process and needs to exit. So usually when you run your conditional statements or your loop statements, you hit the exit automatically. That's when it terminates and gives the right solution to the parent. Now the process resources are deallocated by the operating system. So that resource that was used by that child is being taken away and kept for another process to use it. Parent may terminate the execution of a child process. 1. If a child has exceeded the allocated resources, a parent process may terminate it because it's affecting other processes. Then a task assigned to a child is no longer required, then the parent may terminate that child. Now, if a parent is exiting, the OS does not allow child to continue if parent terminates. If the parent automatically terminates or the grandparent terminates, all child processes terminate. All right, so called cascading termination. So every child starts terminating, right? And very essential. So we have looked a lot at processes. Now let's look at threads, which is same thing, like similar to process, but let's see. Processes do not share resources well. There's a high context switching overhead. That's what happens there. Each process, you need to shut down one process, save it, remove it, before you load a new one. So that creates that context switching overhead that we discussed earlier. And that is a waste of CPU time. So now threads are being created. So the idea is that you separate concurrency from protection. You can allow two or more processes to create, a process can create threads and then they are working concurrently. All right, so you separate concurrency from protection. In multi-threading, you have a single program made up of a number of different concurrent activities. A single program made up of a number of different concurrent activities. A thread is a lightweight process. It is the smallest unit of a process. A thread is just a single unit of a process, right? The basic unit of CPU utilization, it consists of counter, register, stacks, and stack space. A thread shares the following with peer threads. One is the code section, the data section, the operating system resources. It has no protection. There's no protection between threads. Okay, they are running together and they're collectively called a task. A heavyweight process is a task with only one thread. That's all we need to know. We're going to explain further on how threads are and how threads work. Now let's look at single and multi-threaded processes. Now this is a single thread, right? This is a single threaded process. Now this single threaded process has its PCBs information here, the registers, the codes, the data, the files, the memory location, the stack, all information within that thread. So that thread is carrying all the information it needs and usually heavy. Now threads encapsulate concurrency. They encapsulate concurrency. They are an active component because they are the ones that they are executing. Address spaces encapsulate protection. All right, that's the passive part. And then keeps buggy program from trashing the system. Buggy program from trashing the system. Now let's explain this. Now you have this system here. These are three different threads. All this is a multi-threaded process. So it's one process that has multi-threads. And each thread is doing something. Each thread has its own code, registers, its own stack of instructions and all that. Then, now these three threads share code, data, and files. This is what it is within one code and data and files. But when they are processing, this thread has its own register, this one has its own register, this one has its own register, and this is the third. It has its own, they are stored in different locations. So it's the address spaces that encapsulate protection. It makes them protected from each other while they are working concurrently. The advantage of it is that it keeps buggy program from trashing the system. Now, a buggy program, most times, you have a program that runs and needs I/O regularly or needs to perform something before the next another thing is performed. Now, you can have this one of the threads running at the same time, producing its solution, and then this process one could pick it up and then keep on working. So they don't need to wait and go out to do I/O and come back and keep on waiting. You have all the processes running almost together as and when necessary, and then they can all solve the problem faster. That's the advantage of the multi-threaded process. The benefits of using threads is one, responsiveness, two, resource sharing. They have economy, because it's cheaper since they are using more resources, they are sharing more resources. So you don't have to, it makes it possible for you to use fewer hardware resources to do more jobs. Then also utilization of the microprocessor architectures. That's one of the advantages. Now, in a multi-threaded task, while one server thread is blocked and waiting, a second thread in the same task can run. A second thread in the same task can run. So you can have multiple threads, 3 threads, 4 threads, and maybe thread 1, while thread 1 is running, thread 2 needs to wait because it needs a process, but thread 3 does not need anything. It can still be supplying the entire parent process with information. It can keep running. So we don't have to wait for 1 to finish its own, 2 to finish its own, wait for its task, wait for IO, or wait for whatever blocked it, then come back. We don't. 3, 4, 5 can still be running while 1 is doing whatever I want to do. Now this makes a cooperation of multiple threads in the same job confers higher throughput and improved performance, as we have seen before. Applications that require sharing a common buffer, that is, producer-consumer, benefit from thread utilization. We will explain producer-consumer later. Threads provide a mechanism that allows sequential processes to make blocking system calls while also achieving parallelism. It provides a mechanism that allows sequential processes to make blocking system calls while also achieving parallelism. So you see, it can allow a process to stop some threads to run system calls while the other ones are still running. So you have, take for instance, maybe you need to prepare items when you are cooking. Now there are some items you have to prepare before you cook. For example, someone say steam the meat is ready, get the fish ready and everything. Those ones have to be ready before you start the stock. You get the stock out and you start working on your vegetables and all that. But while you're working, while you put your water on fire and then we put the meat, you can go ahead and be preparing pepper and salt and all that later because you're adding them as the process already gone. So you don't have to delay grinding your pepper. You don't have to delay cooking the food because you are going to grind pepper. You can start the food because it's not going to take much time to grind pepper and all that. Same now, let's see a thread state. States shared by all threads in process or address space. Now, one is content of memory, right? Content of memory. They share contents of memory and they share IO states. That's what they share. Now, the states that are private to each thread are the thread control block. Now remember, we have process control block for a process. We have thread control block. So this is private for each thread. The CPU is private. The execution stack is also private. Now you have parameters, temporary variables, and all that. They are all private to that thread. It returns return pieces are kept while call procedures are executing. All right. So let's look at next slide. Thread in context switching still requires a register set switch, but no memory management related work. All right. Thread context switch still requires a register set switch, but no memory management related work. Remember that context switch is when you stop one process, save it, and pick up another process. That is context switch. That idle time is a context switch. The process of stopping a process and picking the next one. But for thread, of course, the register, we may have to pause a register and when you are running the switch, but you don't have to do the whole memory doesn't have to be switched from one memory to another, or you don't have to save one to one memory and move to the next, because remember, by the time the process started, it collected all the memory locations that it needed at once. So because it needed all those memory locations, automatically it doesn't need to look for more memory spaces. These thread states are already blocked, running, and terminated, similar to process states also. Threads share CPU and only one thread can run at a time. No protection among threads, right? Examples of multi-threaded programs. Embedded systems have multi-threaded programs such as elevators, planes, medical systems, wristwatches, single program, concurrent operation. So all these have embedded systems. You have those your microchips in there that have their processes that are running. You just use multi-threads run there. Most modern operating system kernels also run multi-thread programs where they have internal concurrency because they have to deal with concurrent requests by multiple users, but no protection is needed within the kernel. In database servers, we also use multi-threads where you need access to shared data by many concurrent users. Also, background utility processing must be done. You also use it in network servers where you have concurrent requests from network. We also use it in parallel programming where you have more than one physical CPU. In parallel programming, multi-threaded programs are used. One is to split program into multiple threads for parallelism. This is called multiprocessing. So different processors can even work on different threads depending on the architecture of the system. All right, so let's look at this issue of real operating systems. Real operating systems have either one or many address spaces. They have either one or many address spaces and one or many threads per address space. So you see that. An example of one that has one thread, okay, one thread per address space, that's one-on-one, is MS-DOS. Just MS-DOS had one thread per address space. Then we had the one that has many threads to one address space in embedded systems like Java OS, Pilot PC, and all that. Then we have many to many threads to many addresses in traditional Unix. And then for, many to one thread is traditional Unix, while many to many is Mac OS, Windows, and all that. Let's look at the types of threads. We have kernel supported threads, we have user level threads, we have hybrid approach thread also. So a hybrid approach implements both the user level and kernel supported threads. An example is your Solaris 2. Now the kernel supported threads, also called kernel level threads or KLTs, are threads that are fully managed by the operating system kernel. I've already explained the kernel. The kernel is the core of the operating system, where all the memory management, processor management, and file management and others are dwelling there in the kernel. So the kernel is the core of the operating system. So the KLTs are threads that are fully managed by the operating system kernel. Native threads are supported directly by the kernel. Every thread can run or block independently. One process may have several threads waiting on different things. All right. The downside of kernel threads is that it's a bit expensive because you need to make a crossing into kernel mode to schedule. So each time you need to run the threads, you need to move into kernel mode. And kernel mode means you're moving into super user or administrative mode. Example, Windows, Solaris, Linux, and Mac OS all have kernel threads. Then user threads are supported above the kernel via a set of library calls at the user level. Thread management is done by user level threads library, right? Thread management is done by the user level library. The user program provides a scheduler and thread package You may have several user threads per kernel, and user threads may be scheduled non-preemptively relative to each other. Now, non-preemptive means that you cannot stop it. User threads may be scheduled in such a way that it cannot be stopped. Once it starts, it must finish. You pick the next one. So it may be scheduled non-preemptively relative to each other. Only switch on yield. All right. Yield means that you have completed what you need to do. You now switch, or your time is up and you now switch. So the advantage of user threads is that it is cheap and fast. Using such threads is cheap and fast. We don't need so much resources from memory and file resources so much for user threads. Threads do not need to call operating system and cause interrupts to kernel. That is it. That's the advantage. The advantage is that if kernel is single-threaded, system call from any thread can block the entire process. That's the advantage. Okay? If kernel is just single-threaded, that is only one kernel, one thread, then the system call from any thread can block the entire process. So that's why having only a single thread is a problem. It's a real problem. All right? Let's go back. Example of thread libraries are for 6P threads, Win32 threads, and Java threads. Let's look at the multi-threading models that are available. We have the many-to-one multi-threading model. All right, here many threads using one kernel. Many threads are using one kernel. This is similar to say many cooks using one kitchen turn by turn. You have many cooks using one kitchen turn by turn. Now, if many cooks use one kitchen turn by turn, it means that every cook has to go in, cook his own meal and finish, get out of the kitchen, the next one goes in and cook before they keep going in turns until they finish cooking. So that's why you have many threads using only one kernel. You have only administrative right. Only one person can have administrative right at a time. Now, one-to-one means one thread using one kernel. One cook using one kitchen individually. Now, this one is more advantageous because it means that we can have multiple kernels and one thread will work with his own kernel. But remember that this will also be expensive because you have to use more resources also. Then you have many-to-many. In many-to-many, many threads using many kernels. Many threads using many kernels as another multi-threading model. In many-to-many, many cooks, example is many cooks using sharing many kitchen. Many cooks sharing many kitchen. Now, many cooks sharing many kitchen, the kitchen may not be one-to-one, as in one-to-one, you could have 5 threads, 5 kitchens, all right? 5 threads, 5 kernels. But in many-to-many, you could have 10 threads and only 5 kernels. So they just interchange and be using it until they use it. That is also efficient because not all the time that all the threads are always busy. So there's no need giving each a thread. It's only when you're busy. So here's a diagram representation of it. Many user level threads are mapped to a single kernel here. You can see the different threads, 1, 2, 3, 4. All the user threads are mapped to one kernel. So it's one kernel of the operating system that will handle all these different threads. One thread will handle all the threads. Example is Solaris green threads and GNU portable threads. Now let's look at another one, one-to-many. Each user level thread maps to kernel thread. You see, these are all different threads and they're all mapped to the kernel. So this is like each user thread mapped to zone 1111. Example in Windows 10, we have that. Many-to-many model allows many user level threads to be mapped to many kernel threads. So here we have something like 1, 2, 3, 4 threads, and we have only 1, 2, 3 kernels, right? This is a situation. It allows the operating system to create a sufficient number of kernel threads. All right. Now, in this situation like now, we have 1, 2, 3, 4. But all the 4 are tied together and shared among 1, 2, 3 kernels. kernels. So each has its own turn. You can have all the different, you can have more than that, and then you have their own turn with the kernel, right? Example, Windows NT 2000 with the thread fiber package. Let's look at threading issues. Some operating system threading issues. One is the semantics of fork and exec system calls. That's the what does it really do. For example, we say fork and it may give us child processes, and in the process of bringing up the child processes, it may form what may not really be able to be handled by a system. So sometimes we have our systems tend to either crash or shut down because of some of these commands. But as modern operating system keeps going, it gets better and better. We have thread cancellation, we have signal handling, thread pools, and then we have thread specific data. That's some of the problems. Now, let's look at multiprocessing, multi-programming, and threading. Multiprocessing, programming, and multi-threading. Definition: multiprocessing means it has multiple CPUs. Multiprogramming means that there are multiple jobs or processes that can be done at a time. Multithreading means there are multiple threads per process. The question now is, what does it mean to run 2 threads concurrently? All right. You have the scheduler is free to run threads in any order and interleaving, which means you have first in, first out. You have random way of arranging threads in different ways. So it means 2 threads are running together. 2 threads are running together. For example, we have a multiprocessing where we have 1, and then we have 1, 2, 3. These are different threads running together. The dispatcher can choose to run each thread to completion or time slice in big chunks or small chunks. That's left for the dispatcher. So we have here process. We have different processes here, multiple 1, 2, 3, and then this is shorter, this is longer, and this is shorter time burst. Now, if we were to arrange this in the order of, let me say we were to arrange this in order of first in, first out, means A will start first, take his own time, B will start second, all right, and take a long time before C will come in. Let's say these are 3 different processes, A, B, C. They arrived at the same time within the system. So these are multiprocessing, but multiprocessing means that you have multiple processes in. So A runs B, this and that. Now in a situation where you have all these different jobs can be done almost together, what happens is that you now share the time among equal time among A, B, C. Let's say the time is X. You allocate X time to each process. It means, let's say our X could be maybe 3 nanoseconds. So A runs for 3 minutes, you now pick B run for 3 seconds, sorry, milliseconds. Let's do actual time, milliseconds. So A runs for 3 milliseconds, B runs for 3 milliseconds, C will now run 3 milliseconds. Now you pick A again, pick B before you pick C, and then finally pick the last batch of B and run to finish it because there is no other process to run. Now this is an example of running multi-program. Everybody is having a bite of the time. Multi-programming. We have cooperating processes. Concurrent processes can be independent processes, which means they cannot affect or be affected by the execution of another process. They are independent. We can also have cooperating processes, means it can affect or be affected by the execution of another process. So one process could be working and then its output affects the input of another process. All right. That's one of the things in programming. Whereas they can, if it's an independent process, it doesn't affect, it just does this thing and goes. But in cooperating processes, it means that one process affects the next process. So the advantage of process cooperation is that information sharing is made available, computation is speed up. You have a modularity because each of the different process within the process is modular. It's a fully well coded, like what we call object programming to object-oriented programming is modular. Convenience, editing, printing, and compiling. That's the advantage of cooperating. All the processes are, instead of, that's where, you have concurrent execution advantage. The concurrent execution requires process communication and process synchronization. They must talk with each other. Now let's look at this process, interprocess communication, because one process must talk to the other before they can fully enjoy processes that are cooperating with each other. We have a situation where we have like process 1, process 2, and process 3. These are like 3 processes that are communicating with themselves. All right. Now, this process have separate address space isolates processes. Separate address spaces isolates processes. High creation and memory overhead is the disadvantage of having separate address spaces for each process. All right. The relatively high context switch overhead. Separate address space because you have to switch from this process to this process, from this process to this process, keep on switching whenever you need this process. If something process 1 needs something from process 2, you must do context switching. Because it needs from 3, it has context switch. If 2 later needs something from 3, and all that. Especially when there are system calls, conditional statements, and all those calls. Now, mechanisms for processes to communicate and synchronize, all right, are available within the operating system. Let's say we use through shared memory. It is accomplished by mapping addresses to common DRAM, read and write through memory. All right. So if process needs to be process needs to communicate with each other, we need to be able to use that for them to understand how they can do it through their memory. All right. Another option is by using messaging system. Because process communicate without resorting to shared variables. Process communicates without resorting to shared variables. Instead, they use what we call send and receive. These are the send and receive messages, and it can be used over the network. So in this situation, if a process needs information, it places a send, and when it gets information to consume, it receives it and says I've received it. Messaging system and shared memory is not mutually exclusive. Messaging system and shared memory are not mutually exclusive. Mutually exclusive means that there is only one that can occur at a time. For example, similar to what we have a printer. Once you send your job starts printing. No other person can print apart from you. That's what we mean by mutual exclusion. Okay? So here, messaging system and shared memory means that each job can be sending message at any time, then it can be sharing memory at any time. All right? It's just that there's protection between their memory spaces. All right? So this can be used simultaneously within a single operating system or a single process. Messaging system and shared memory can be used simultaneously within a single operating system. All right. Now, let's look at shared memory communication. In shared memory communication here, this is an example of where we have different programs in their own virtual address spaces, and they are going to send information to another location in memory. All right. Now let's say this is your virtual address space. Okay. This is virtual address space 1, this is virtual address space 2. program 1, program 2 in virtual address space 2. Now, this allocation could be in your hard disk drive. Okay, could be in your hard disk drive. Communication occurs by simply reading or writing to the shared address page. Now, what happens here is that this is your RAM. This is the main memory. This is our RAM, or you can call it the dynamic RAM, DRAM, whatever. This is your hard disk, this is your hard disk. So if the system needs, the operating system needs an instruction, the CPU needs to execute something. Remember, there is a shared space, there's a shared information between these two. For example, it could be an application the two of them are sharing. Now that application is placed within the RAM, somewhere in the RAM as a shared memory. Then the different codes, the code for program 1 are 1, data 1, code 1, heap 1, stack 1. And that for program 2 are code 2, heap 2, data 2, and stack 2. Now all these are being placed within RAM. Now you can see that there is a demarcation between them because these places are different memory locations. Let's say this could be location address 0, location address 50. This is just for understanding. So if the system needs information from about program 1, a table is being created that says program 1 is stored somewhere in memory. So the system goes there to pick, it goes there to read from this RAM. So the system does not always have to go to the hard drive to pick it. It picks from the location in RAM and then executes it. Okay? So communication occurs just by simply reading and writing. And once it's through, it can modify the code. It can write back into this memory again. And it can keep working like that so that the two program A can take something from program 1 can take from 2, program 2 from 1, but they're all well arranged here. Now there's a table that keeps tab of them. And that table will tell the exact location that each of the data we are looking for is. The code we are looking for, the data we are looking for, and all that. So there's really low overhead communication, and it introduces complex synchronization problems. Okay? There are some complex synchronization problems. Because cooperating processes, let's look at cooperating processes and let's look at how they handle message passing, how they cooperate using message passing, right? Interprocess facility provides two operations. Interprocess facility provides two operations. The operations are send and the next one is receive. So you have send message, the other one is receive message. Now the send message, the message size can be fixed or variable. So the sender sends, it raises a system call to send a message to it, and then when it receives it, it drops a flag. So the send raises a flag to ask for data, and then when it receives, sends it drop the flag. That's the receive sign. So if processes P and Q wish to communicate, they need to establish a communication link between them, and then exchange messages via the send receive. So as I said, messages can be different size. It could be fixed, it could be variable. The fixed messaging size is straightforward physical implementation. The programming task is difficult due to fragmentation. Right? Then variable message type size means you have simpler programming. More complex physical is more complex to actually, code it and manage it, and then you have physical implementation. Right? You will see, fragmentation is when you have spaces but you cannot fill it because of some limitations within the algorithm or within the system. So we will meet more on that when we talk about memory. Here are some implementation questions of how do we get processes, to interact with each other. How are links established? Can a link be associated with more than two processes? How many links can there be between every pair of communicating processes? What is the capacity of a link, fixed or variable size messages, unidirectional or bidirectional links, and all that? So these are some of the problems that I encountered. And then the problems have to also be solved as we move on. But we are just going to talk about a little bit here, but further lectures we are going to have a more in-depth knowledge on how we have interprocess communication goes on. All right, let's look at direct communication. Sender and receiver processes must name each other explicitly. The send P, message equals to send a message to process P. So you must name, I need send P, send the message to P. Then receive Q, message, receive a message from process Q. All right, so this must be explicitly named. Properties of communication link. Links are established automatically. A link is associated with exactly one pair of communicating processes, exactly one link between each pair, and link may be unidirectional, usually bidirectional. Link may be unidirectional, that's just one way. It is usually bidirectional, which means you can send a message to another process. The other process can also receive it and tell you, I've received it, send you back a message, I have received it. But there's also a possibility of while P is sending a message to Q, Q is also sending a message to P at the same time. So that's bidirectional. They can be communicating together. That's how the system works. Now let's look at indirect communication. Indirect communication. Messages are directed to and received from mailboxes, also called ports. That's indirect communication. They use ports. Messages are directed to and received from mailboxes. Here we have unique ID for every mailbox. Processes can communicate only if they share a mailbox. For example, you have here send a message. You're sending a message to mailbox A. Then receive a message, receive message from mailbox A. You have this kind of thing now. Now, instead of receiving, remember, below had the other one we says send direct to message, to send P, all right, the message directly. But in indirect, we are sending it to the mailboxes, all right? We are sending it to the mailbox A, which the process that needs it will go and pick its own message from the mailbox. Now, the mailbox acts like a buffer so that there is the advantage of not creating so many interrupts in the process of sending messages. A process can still be running and then ask for a message, and then the message is sent as a mailbox, and then it arrives at the mailbox and stays there in a buffer until when the process that asked for it sees it, receives it, and then sends the signal, I have received it. Now, properties of the communication link here is that the link established only if processes share common mailbox. Link can be shared with many processes. Pair of processes may share several communication links, and links may be unidirectional or bidirectional. So indirect communication using mailboxes, this is it. P sends a message to mailbox A, and then Q picks it from mailbox A. Then Q sends a message to mailbox B, while B also picks it from here. You have there where they use message to communicate. The operations of the mailbox is that you create a new mailbox, send or receive messages through the mailbox, and then you destroy the mailbox. That's the operation using mailboxes. The issue here is that the mailbox sharing is that P1, P2, and P3 share mailbox A. P1 sends message, P2 and P3 receive. Who gets the message? That's the problem here. If they are sharing, P1, P2, and P3 are sharing a mailbox. P1 sends a message, P2 and P3 receive. Who gets the message? So who actually supposed to pick up the message? So a possible solution is disallow the links between more than two processes. Disallow the links between more than two processes. Allow one process at a time to execute a receive operation. Allow system to arbitrarily select receiver, and then modify the sender. So that's what happens. You have to, let's say this situation now, you have different mailboxes, all right, for different processes, all of them in one link. You have to allow only one process to come at a time and pick his own message. So two do not receive it at the same time. Only one will receive notification of his own message. As I talked about message buffering. Now, the link has some capacity to determine the number of messages that can reside temporarily. All right, it has the capacity to determine the number of messages that can reside in it. The queue of messages attached to a link. We have different messages that are attached to one link. One of them is zero capacity. This one queues is 0 messages. The sender waits for receiver. Synchronization is called rendezvous. So the sender waits for the receiver, which means we're talking about the situation here where the queue of the messages are attached to a link. Now let's say the queue has nothing, all right? There's nothing in the queue, no message at all. So we call it zero capacity queues. Bounded capacity queues. You have a final length of n messages. Final length of n messages. That means the sender waits if link is full. These are important concepts to understand when we talk about the messages for interprocess communication. Then we have unbounded capacity, where unbounded capacity queues where there's infinite queue length. The sender never waits. These are different methods in which the messages can be handled. One is that when the queue is 0, that means no message, then the sender can receive a message. But when it is full, then the sender will have to wait and then send, and you'll keep on checking if the queue, if the mail is 0. Keep on checking. If the buffer is full, then don't send any message. The buffer is empty, you send message to it. But in unbound on, you can keep sending all the messages because there's excess space for you to keep sending as much message as you want. So let's look at message problems, exception conditions. Message problem, exception conditions. Process termination. Process termination. The problem is P sender terminates, Q receiver blocked forever. This is a problem. Let's say P sender terminates, stops, and Q sender blocked forever. The receiver blocked forever, that means it doesn't want to receive anymore, while the sender has stopped sending. There could be that problem where there's a process termination. As there's a problem within the system. Then the solution is the system terminates Q. Must terminate Q, process Q. The system notifies Q that P has been terminated because P had terminated. P was the sender and it terminated. There are two processes here, P and Q. And P is the process that was sending messages to Q. Then, after it finished sending, it terminates. Q, the receiver, is blocked forever because it has received a message from Q, but it could not send back to Q that I have received your message. So it keeps waiting, block that place forever because P has not told you, okay, you can empty it, I have gotten what you wanted. You know, there's a communication, there's a handshake between the different processes. So the first thing is to solve this kind of problem, exception conditions. You first of all terminate Q. Then the system notifies Q that P has terminated. P has an internal mechanism or a timer that determines how long to wait for a message from P. All right? He has an internal mechanism that determines how long you wait for me. So if the time is up, automatically queue will open up. That's one of the ways to handle such a problem. That's one way to handle such a problem. There has to be a timer. It's either one, you terminate queue, notify queue that P has terminated, or the timer is set up, then you end the process from pinging queue, looking for answers. Now there's another problem here. The sender sends message, queue receiver terminates. The sender sends a message and queue terminates. Now, in automatic buffering, P sends message until buffer is full or forever. In no buffering system, P blocks forever. Because in automatic buffering system where there is a location for it to keep storing, it keeps sending the message because it has not received any information from queue that it has received what is sent. Remember that when it sends information to queue, queue must also respond back that it has gotten the information to P. So if it does not receive the information, P will keep sending that message until the buffer is full. Or if you are looking at infinite buffering, it keeps on sending until forever, keep sending and sending and sending, and at the end of the day, we have nothing to, no response, never gets any response. Then the second one is, if there's no buffering at all in that scheme, then P automatically will block. P blocks forever because it has sent out a message, it has not gotten any receive, so it just blocks, locks up there and doesn't send any message again. So it freezes. So in such a situation, how you handle it is that the system notifies P that queue has terminated. Notifies P that queue has terminated. So P just, stop sending the messages. The system terminates P. P and Q use acknowledgement with timeout, or they use a timeout where you don't get acknowledgement, you stop sending, right? So those are different ways of handling these exception problems, which are things that you can face within the operating system. Now let's look at another problem, is lost messages. What if you send a message and the message gets lost? How does the operating system ensure that that message can be gotten back? One is that the operating system guarantees retransmission. So that is why you see it keeps sending. The sender is responsible for detecting if using timeouts, right? For example, it keeps sending and sending and sending until operating system will notify it that that message is lost. Okay. For example, P can say, I need this message, and P sends to Q, and Q does not respond back that I've gotten it. Q will keep sending until the OS does otherwise. The second option is that sender is responsible for detecting if using signed out. So if the sender is timed after sending, and there's a timeout, you can go ahead and just stop sending. Then the sender gets an exception telling it that the message is lost. Okay, that's another way. What of scramble messages? How does it handle scramble messages? Messages arise from the sender P to receiver Q, but information in message is corrupted due to noise in communication channel. That's scramble message. The solution is we need an error detection mechanism, which we call checksum. One of them is checksum. Secondly, so the error detection notifies that since there is that message is corrupt and therefore should be resent, then need error correction mechanism so that it will handle the transmission. So those are the two mechanisms that are available to handle that. Let's look at another problem, the producer-consumer problem, which is available when we're talking of two processes communicating with other, because we are dealing with inter-process communication here. How are they going to communicate in such a way that they would know, just like you have on a network? If I send a message to your computer should be able to tell my computer I have received the message. All right. Then your computer, I will stop sending the message. Else, we'll keep sending the message until maybe there's a timer that says don't send anymore. If you notice sometimes when you want to maybe connect, you want to make like and a connection on your device, maybe to your internet Wi-Fi device. You click on it, it runs for a while, keeps pinging your device to see if it connects to the internet. Your device does not respond. It keeps pinging for a while. Sometimes we even tell you how many times it needs to ping it. Sometimes one will say ping it for 60 seconds. It keeps pinging your device until if it doesn't get any response, it stops pinging you. All right? Else it would have been pinging forever. That one uses timeout. Now let's look at the paradigm for cooperating processes. The producer produces information that is consumed by a consumer process. All right. Then we need buffer of items that can be filled by producer and emptied by consumer. We need a buffer. The producer is P. Let's say process P. He's sending messages for Q. Right. So we say that the producer produces information that is consumed by consumer. Let's take, for instance, we have P, as we said before, and we have Q as a consumer. All right. We need buffer of items that can be filled by consumer and emptied by, can be filled by producer and emptied by consumer. Like I explained before, there's an unbounded buffer. Unbounded buffer places no practical limit on the size of the buffer. Consumer may wait. Producer never waits. It keeps dumping whatever message it needs in that. Then we have bounded buffer that assumes that there's a fixed size. There's a fixed size. The consumer waits for new item. Producer waits if buffer is full. All right. So there has to be a way that the producer and consumer must synchronize. How do I know that buffer is full? I should stop sending. Or how do I, the consumer knows that it has been dropped and he has to go and pick up. So let's look at this situation here. Imagine a simple scenario, a donut shop, right? Donuts are the data items or messages or files. All right. The producer is the baker who makes donuts. A thread process creating process. A thread or a process creating data is a producer. Thread or process creating data is a producer. So you just imagine like you have a baker who bakes donuts and the consumer who eats donuts. Now, the baker just bakes the donuts and drops it on the table. And the table has a limited space of, say, 5 spots for donuts as a shared memory. Now, let's say we have that kind of scenario here, right? You have a baker, he has a consumer, and then the consumer sits on the table. He has to put 5 donuts, and the consumer has to eat. So our producer is the one creating the data, while our consumer is the one using the data. And the table is a shared memory location, or we can call the buffer, right? So the question now happens is this. What happens if the baker or the producer makes donuts and puts them on the table? He puts them on the table, all right? The consumer takes donuts from the table and eats them. But if the table is full, the baker must wait. He can't keep placing them again. The table is empty, the consumer must wait. This is the producer-consumer issue. So if I cannot keep producing when there's no space to put it again, there's no space to put it again. And if there is no food, the producer must wait. So the question now is, if I have placed donut on the table, which is the data that is being produced, or the producer is shared into memory, and then he does not see anywhere else to put it, what should happen next? He will go and wait. How would the consumer tell it that, look, okay, I've started eating this stuff, can feed him more? Because we are looking at a situation where we are not talking about unlimited table here, all right? So the problem, how do we make sure that the producer doesn't put data into a full buffer? That's number one. How do you make sure that the consumer doesn't take data from an empty buffer? Those are the two. And both do this without messing each other up. This is where synchronization comes in. To avoid problems like that, synchronization comes in. So to avoid problems like that, data is being, avoid problems like data being overwritten. Because if I come and let's say you have a scenario like the donut and you place it on the donut on the table, then automatically, If there's no more space, let me say we have our 5 donuts here. 3, 4, 5. If there's no space anymore, it's possible that the producer will come and remove one donut and replace it with another one. Meanwhile, the consumer Q has not consumed that donut. So he has lost that information. So that's the problem. So data being overwritten is a problem. Reading garbage data, because if Q comes to read something from there now, it's going to read something that is completely different from what it wanted to read. So garbage data crashes or unexpected behavior. So we use synchronization tools like semaphores. We use mutexes, what we call mutual exclusion locks. We use monitors, high-level languages like Java, to arrange process synchronization. All right. This makes sure that only one thread accesses the shared buffer at a time. Only one thread accesses the shared buffer at a time. The producer waits when the buffer is full, and then the consumer waits when it is empty, just like the case of the donut. So that's how the producer-consumer program are being handled. We can see this is a flowchart of the producer-consumer program. You have where they have a shared buffer here, a shared buffer, fixed size queue. Remember, we are talking about fixed size here. So the producer makes data and dumps it here. The consumer goes to consume the data from the fixed size queue. Now, the producer checks if buffer has space. If it has space, then add item, e.g. donut, then they signal the consumer. Wait if the buffer is full. That's just what it does. Then the consumer now check if buffer has data. Remove item from buffer. All right. If it has buffer, remove item from buffer and signal the producer. But if it's empty, wait if buffer is empty. This is the algorithm that is being used to handle a situation where you have process producing and another process consuming, right? This is the flow diagram of that same process. So we'll move on. And this is an example of a pseudocode to handle the bounded buffer using interprocess communication when we talk about messaging. But the producer here, it says repeat. Produce an item if next P, in next of P. Send consumer next of P. So until false. So it keeps producing and sending to the producer, notifying the consumer that something is there until it sees that it is filled up. So until false. So if it's false, automatically it will stop. Then consumer says repeat. Receive producer next C. It keeps on consuming item from next C until false when it notices that the producer is now empty. All right. So that is it. This is bounded buffer shared memory solution. We have a code. These are the codes that are being used to run it. For example, we have in a variable here, we have var n type item is equal to whatever quantity you want to put there. Var buffer, we have an array is between 0 and n minus 1 of item. In, out, like two things is between 0 and n minus 1. In is equal to 0. So initialize in to be 0, initialize out to be 0, use a shared buffer. Is a shared buffer that is going to be used for all ins and out. It is a circular array. So buffer empty if in is equal to out. So buffer is empty if in is equal to out. All right. Buffer is full if in plus 1 mod n is equal to out. So if it does that, it's a do nothing, no operation. So nope means do nothing or no operation. All right. So that is the way it's being coded, and you can do that in any of the languages of your choice, either in C, in Python, or whatever. Right. Please, producer creates field buffers. Producer process creates field buffers. Repeat. Produce an item in next P while n plus 1 mod n is equal to it out. Do noop. Noop means no operation. offer in is equal to next p of next p. In is equal to in plus 1 mod n. So this is our producer situation here. As far as it is not false, you keep adding in plus 1, incrementing until it is false. All right, that means there's no more space again to add into the buffer. All right, then same thing here with the consumer. Please like, share, and subscribe to my channel. And if you have any question, please drop it in the comment section and I'll get back to you. Help me to share it because it will help the algorithm. Subscribe to the channel so that others can also see it. All right, have a good day. Bye-bye.